Thank you very much for giving me an opportunity to have a talk today. So my talk is about fractional powers of Bessel operator, and I studied differential equations and fractional powers of Bessel operator very long time. So according to this event, I was wondering that I can find some applications and I can use something, some stochastic things and connect and combine and find generalization of my operators in this sphere. Here you can see this singular Bessel operator of the second order, and of course you can see this operator if you tending to spherical coordinates in the Laplace operator, and if you have here gamma is equal to n minus 1, where n is the dimension of the Euclidean space, or any space where you can consider your Laplace operator, you will obtain this one-dimensional Bessel operator. But also, if you open some books about applications in physics, in acoustic, in some mechanical problems, you can find also this differential operator. Also, when gamma is not equal to natural number, but when gamma is equal to 1/2 to 1 divided to 3, when gamma is equal to also minus 1, actually, it is all of these are quite applicational things. And here we have singularity, and also Euler-Poisson-Darboux equation has such operator in one side of this equation. Here I would like to introduce you fractional powers of such operator. This fractional power in his kernel has a so-called hypergeometric Gauss function. And this is the presentation of this function. It is a series, and of course here we can see the integral representation. When we would like to construct fractional power of the Bessel operator, as usual, we can start from the integral operator, so fractional integral, so-called. It is negative real power of the Bessel operator, and it is defined by the formula 5. Of course, as in classical case, we can consider left-sided, right-sided fractional Bessel integrals, and also we can consider such operators in the segment or in the actually semi-axis, of course, because you know that since we have singularity at 0, all our function should be even with respect to all variables where we have Bessel operator, because if they are not even, then all our solution can be not continuous. So as usual, we define positive power of this operator by 6, so-called it is computer type way to define this positive power of the Bessel operator, because here we have just iterated Bessel operator, and here we have integral operator shift to this n. Also, we can consider so-called Riemann-Liouville type when Bessel operator, iterated Bessel operator is in front of the integral operator. But here, since I would like to consider differential equations of fractional order, it is, of course, as you know, it is Professor Podlubny told many times, and is in his famous book was presented. Probably it was the first such book where this idea was presented, that computer derivatives has many applications, because the initial condition when we use computer derivatives is very simple and very useful and has real applications. And of course, you know, if we consider computer derivative and we consider the solution of such equation with computer derivative at 0, you can obtain the Cauchy problem. But when you consider Riemann-Liouville derivative and initial condition in 0, won't give you real Cauchy problem. So here, of course, when n is equal to natural number, we have this operator. And what was the first? As I think the first work about this connected with the fractional power of Bessel operator was the paper of Ida Sprenghuysen-Cooper, and she wrote this nice paper, and also the way how she obtained this form with the hypergeometric function, the kernel, was presented in this paper. It is very nice, because we can see how this strange kernel, probably quite complicated kernel, was appeared in this operator. The next paper was written by McBride. It is also a really nice paper, because in his paper he considered not only powers of Bessel operator, but so-called hyper-Bessel differential operator and its fractional powers. And he, in this work, in this paper, obtained a lot of basic results. And of course, we can take them for our case when we have only one Bessel operator, not, you know, hyper-Bessel operator. Next, Professor Kyriakova and Professor Dimovsky obtained a lot of results about operational calculus and about general forms of fractional operators, including hyper-Bessel differential operators, and also they associate this operator with Abreshkov transform. It can be found in their books and the works as well. Here we can see Adam McBride and Ida Sprenghuysen-Cooper, and we can see who were their advisors. It is also very famous people. And Ivan Dimovsky, as I understand, he actually do not has his supervisor, as we can in regular sense. And Professor Virginia Kyriakova, very well known for the fractional world. So McBride in his paper present this space, these spaces, and according to these spaces, he obtained this theorem, which I just rewrite to my case when I consider not hyper-Bessel operator, but just Bessel operator. And we can see here that we have spaces, and we can work with this operator. Also, we have, it is now my results, which were published here, just simple properties when we put gamma is equal to 0. In our case, we should obtain, when in Bessel operator we put gamma is equal to 0, we obtain just second derivative, and here we just obtain, you know, Riemann-Liouville fractional integral, so it is, of course, sensible. And next, the idea which we should use in our fractional world, that practically every fractional operator should be obtained as some factorization of simpler operators. And here we have some such factorization, here so-called Erdős-Kubert fractional integrals, and using these two Erdős-Kubert, we can obtain our one negative power Bessel operator. Also, Mellin transform is very useful to work with our operators, and here we can see how this Mellin transform acts to the integral operator, to Bessel integral operator. The next one result, Professor Kiryakova and also another researchers who studied fractional powers of hyper-Bessel operator and Bessel operator, they have never solved equations because they just didn't have the instrument. The main instrument to solve equation is, of course, integral transform. And I found this transform, maybe it is not some extremely great result, but using some formulas, integral formulas, I just can find this integral transform. So a little bit improved Meijer transform with the Bessel function of the second kind, modified Bessel function of the second kind in the kernel. This transform more or less very well known, and this transform is connected to Laplace transform, and as for inverse operator, we can see it is not very convenient every time when we see this integral. It is not very convenient to, you know, real life applications. That is why I a little bit change this inversion. I used Poisson operator, so-called transmutation operator, which is connected to the Bessel operator and the operator of the second derivative just. And using this inversion with, again, Buchmann-Erdős operator, I obtained new representation of the inverse operator of modified Meijer integral transform. And using this modification, for me, was really easy to solve equation with fractional powers of Bessel operator. Here we can see that how this Meijer integral transform acts. So it is very, of course, easy and convenient. Practically, you know, the same as Fourier transform or Laplace transform. Of course, when we have not integral operator, but differential operator, here iterated Bessel operator, we can see that we obtain this sum in formula 13. It is the simple way, because here this should be bounded when gamma is not equal to 1, and when gamma is equal to 1, we actually the logarithmic case was obtained, and it should be this relation with the x of power beta. But this formula can be obtained And the final, we can see that this our Meijer transform acts to the fractional power of Bessel operator by this formula. Here we can see just the same situation when we take Laplace transform of the just computer derivative, and we can see here our possible initial condition which we can put in our equations. So here first I was started from the finding this function, and I put this condition, add these conditions to this equation, and also we have additional conditions here. It is the standard situation when we are working with Bessel operator. All odd derivatives at 0 should be equal to 0, because we have the singularity at 0 multiplied by the first derivative. So all odd derivatives should be equal to 0 at 0 in order to obtain continuous solutions. Here we can see the theorem that fundamental systems of solutions to the equation 16 here has this form with psi function, and this psi function is presented, where is it? Sorry, probably I didn't put this psi function to this presentation, but actually it is just generalized. It looks like generalized hypergeometric function. You know, some gamma function in the series. By the way, this function should be known, and of course I should put it to the slide. Okay. So the unique solution for the initial value problem 1618 is given by this formula. Of course, using this also psi function. And as an example, in every time I want at each step I want to see the connection to the regular computer derivatives, and here I consider the case first when I not also only computer derivative, also with the case when we have just the first power, and it is just checking of the result. So if I put alpha is equal to 1, I should consider just Bessel function of the first kind, and here after working with this, of course, I obtain using some calculations, I obtain that this function is appeared, and this function, it is just normalized Bessel function, which is looked looks like this, and it is the good thing for me. Also, when we consider another example with sometimes it called Jabarshan-Caputo, sometimes it called just Caputo fractional derivative. When gamma is equal to 0, we should obtain just this equation with Caputo fractional derivative. And here I can put gamma is equal to 0 and just find the solution. When alpha is from 0 to 1, we obtain just one term of our sum, and we can check it. So the results connecting transmutation operators and different results connecting to Bessel operator. Actually, this subject connecting with one-dimensional operators is not really very well studied. I studied more multidimensional operators like fractional power of Laplace Bessel operator and the wave operator, fractional powers of wave operators with the Bessel operators instead of the second derivative. But I decided that for this event, one-dimensional case will be more interesting. So another result can be found in these books. And so I think that is all. Thank you for your attention.
Very interesting talk. So any questions?
Hello.
All right. Hello, Virginia.
Can I make a comment?
Sure.
Yeah, the talk is okay. You hear me?
Yes, we can hear you.
Yeah. The talk is interesting, but I have a comment. As the speaker mentioned about that solutions of this kind of equations have been never found explicitly. And actually, it is not the case, because even the Bessel, the hyper-Bessel equations in general linear case are solved in including fundamental system of solutions by means of hyper-Bessel functions, and in terms of the G functions, and especially the equations 16 of fractional order, also in the general case have been found to have a solution of multi-index Mittag-Leffler function. The techniques are also using the general Poisson transmutations, also a kind of generalization of the Meijer transform, the so-called Obreshkov transform, and so on. So these results are interesting as specifications in these interesting cases, but should be mentioned that in the more general case, there are solutions in explicit form. And can you compare it, of course, yes. So it's okay.
Thank you very much, Professor Kyriakou. I will compare it. And also, I have results about generalization of this. Here, I consider only one-dimensional case, and next I consider Euler-Poisson-Darboux equation with the fractional powers, and in my further studies I also based on this my results, but I should compare it with your results as you mentioned. Thank you very much.
So also there are some recent articles published in fractional calculus and applied analysis with some computer methods to analyze the solutions of such kind of equations, which also can be interesting. Not only the explicit solutions that were found, say, before 2000 and after 2002 and so on. So it would be interesting to compare and to mention these results as well.
Yes, thank you. I will do it. Okay, thank you.
Any other questions? Okay, thank you very much. Okay, our next speaker, Dr. Mladen Savov from Sofia.